Physics, School of Basic Engineering Sciences, first year department. Today I will go to teach about the basic concepts of crystals, crystal growth, and what are the characterizations to be done to analyze the crystals. So what do you mean by crystal? So crystal is the regular and a periodic arrangement of atoms which are three-dimensionally arranged in a lattice array. So this is called as crystals. Basically, the solid materials are classified as crystals and non-crystals. We know very well about that there are matter can be classified into three types: solid, liquid and gases. In solid, the material is further classified into crystalline material and non-crystalline material. So how this solid and liquid or atoms are differ from each other means by means of the distance between the neighboring atoms. It is in the order of few Armstrong unit. So this is the first category of crystals. So here the classification of solids are given: crystalline material and non-crystalline or amorphous material. So what is crystalline material? That is regular and periodic arrangement of atoms. So that is called crystalline material. Okay, if you break the crystal, what happened? That means it will be broken into a small pieces of a regular pattern. Okay, so a crystal is a combination of small cells which are identical in shape, size. So if you break it, you can get the small size of same crystal system, same shape. So these crystals have directional property. So what do you mean by directional property? Means if you are taking a material and we are rubbing the magnet in one direction, x-axis direction, y-axis direction and z-axis direction, but you are taking the three same materials and you are magnetizing it. How can we magnetize? You can rub it by x-axis direction, only one direction, this direction, x direction, y direction, only one direction, z axis means only one direction. So you are going to only up one direction, not reverse. So if you are rubbing this material by means of a magnet, this material get magnetized. But compare these three magnetizing samples, only one direction is maximized magnetism, the other two direction is less magnetism. So this is called as directional property. With respect to the direction, the property varies, then we called this is anisotropic substance. So the crystals exhibits anisotropic behavior. So what about non-crystalline materials? Non-crystalline materials, how the atoms are arranged is irregular and non-periodic manner. So irregular means what? One assembly of atom or molecule group and another assembly of atom or molecule group, one with another with equal distance. It is separated and it is aligned with equal distance everywhere in three-dimensional. So the three-dimensional plane it is arranged. But in non-crystalline, they are not periodic. Periodic means the atoms are randomly arranged, the molecules are random combination, and the distance between the atoms or molecule also varies. It is not a constant one. So that is why the atoms or molecules are arranged in irregular fashion, and these materials are known as non-crystalline materials. So the word non-crystalline or amorphous, so is mentioned. Amorphous means without any form. So the word which means that amorphous is without any form. So the atoms are arranged randomly and are not based on the regular repeating pattern. So this is non-crystalline material or amorphous. So without any form. So what are the examples for a non-crystalline materials? Glass, mica, rubber, plastic. So these are all the non-crystalline materials. So these non-crystalline materials are not a direction dependent property. That is why it is called as isotropic. For every direction the property is same. That is why we call these are all non-crystalline materials. So these are the classification of solid into crystalline and non-crystalline materials. So what about crystallography? Crystallography is the study or the branch of science which deals with the crystal structure inside the crystal, how the atoms and the molecules are arranged, how much of bondings between there, how much of bond length is there. So these are all identified by experimental procedure. That means a ray is passing towards the crystal and it analyzes the location of atom, bonding length, etc. By knowing these data, the crystal structure is identified. That means what is the dimension of the crystal, where the atom is located, and where the molecules are located, what is the distance between the atoms, what is the bond length. So these are all identified. So these experimental techniques which helps to identify the crystal structure. That means the location of atoms, the bondings and bond lengths by using various rays. That means where X-rays, electron beam or neutron beam are used to identify the crystal structure. So this branch to identify the crystal structure by passing the rays are called as crystallography. If you are using the X-rays, then it is called as X-ray crystallography. So the phase change from liquid to gas, that is called as crystallization. So how we crystallize? For example, we can discuss this with the natural crystal, sodium chloride. Sodium chloride is nothing but a salt. We are eating a salt, you know. That salt is a natural form of crystal. The chemical formula is sodium chloride, NaCl. How the salt is manufactured? The seawater is collected in the seashore area and it is saved in the land by block areas, and due to the sunlight the water is evaporated, then finally the salt crystals are formed. So this is a slow evaporation technique. The crystallization is possible. So salt is a natural crystal. By means of crystallizing the seawater, we are getting the sodium chloride crystal structure. That means sodium chloride or a natural salt. So this is the process how the natural salt is manufactured. This is called as slow evaporation technique. The process is called as, that means the conversion of seawater into sodium chloride salt is called as crystallization. So what do you mean by crystal? So the crystal is a three-dimensional solid material and the atoms or molecules are arranged in periodic manner in all three directions. So that is called as crystal, and crystallization is the process of making the crystal, and by analyzing the crystal structure by using X-ray is called as X-ray crystallography. So what are the terms used in crystallographic? There are so many terms. Lattice. So what do you mean by lattice? Lattice is an imaginary point, like in common, in the morning, in front of the house, our ladies are using dots and they are drawing column. Okay, 4 rows 5 columns, 5 rows 5 columns, 3 rows 5 columns. So these are all the methods we are following. The lattice points. The lattice points are the imaginary point which are arranged equally spaced points in all 3 directions. So if you are looking every point surrounding the one lattice point, it has the equal number of same environment of atoms. That is called as lattice. So these are all imaginary points which are used to represent the position of an atom. Next one is space lattice. So the lattice points which are arranged in 3-dimensional, that means infinite number of points in 3-dimensional which has the same environment everywhere. So this is called as a space lattice. So what do you mean by lattice points? So in space lattice, every point which are used to represent the position of atom or molecule in a crystal, that is called as lattice points. And the basis, what do you mean by basis or motif? Lattice points are the imaginary point. With the reference of these points, the atoms or molecules are distributed with respect to the lattice point. That means in and around the position of the lattice points. So a group of atom or a molecule, okay, which are identified with respect to the position of lattice, this is called as basis or motif. That means lattice point is the fixed point, but it is imaginary. But the atoms which are combined together to form a molecule with respect to these lattice points, and they are equally periodically arranged. So this group of atom or molecule which are arranged with respect to the lattice points, this group of atoms are called as bases. So what about crystal structure? This lattice points and the group of atom or molecule which is arranged in every lattice points in the 3-dimensional array, so it gives the complete structure of a crystal. So the space lattice and the basis which gives crystal structure. So this is the logical relationship between space lattice and the basis. And what are lattice planes? So we have 3-dimensional material. So a lattice points or lattice line and a lattice plane. Every plane behind and below there may be another plane. So the stacked planes which are repeated in 3-dimensionally, so it forms a crystal. So these planes are called as lattice planes. So what about a unit cell? So what do you mean by unit cell? We are living in a room, building, house, office, whatever it may be. This is a room. This room is constructed by a basic unit of one solid material, that is called as brick. You know very well about the bricks. So after the basement is basement is prepared, then we are keeping the one brick nearby another brick and we are constructing a wall. By using the bricks which are the fundamental least unit of this building, like that a crystal is made up of very small boundary, the smallest volume of a geometrical figure, so which is repeated in 3-dimensional, and the entire crystal structure is derived. So the unit cell is the smallest geometrical pattern of a crystal, which is repeated in 3 dimensions. The entire crystal structure is derived. So this is the fundamental of crystal. So what is the unit of human body? Cell. What is the unit of an animal? That is also cell, because of human, animal and all living organisms which are made up of cell. So the same as the structural building, that is also called as unit cell. For a crystal, it is a bulk crystal, but it is made up of a small unit cell which is repeated in 3 dimensional. The big crystal is formed. So the fundamental smallest geometrical structure of a crystal is called as unit cell. Hope you can understand this by using the bricks and the building. So this is easiest method. And next one is, how can we represent the crystal about their dimension, length, how its shape is. This is decided by means of 2 important parameters, 2 important factors. What are they? Point of intercepts and interfacial angles. So the point of intercepts or the lattice parameter or the cell parameter is nothing but the length of crystal in 3 dimensional axis. So we know very well about that x axis, y axis and z axis. Among these, the crystal is how length in x axis, how much of length in y axis, how much of length in z axis. So these 3 axes, their point of intercept on the x axis, y axis, z axis is A, B and C. This is represented by small ABC. So this is called as lattice parameter or cell parameter or point of intercept. And another one, interfacial angle. So what do you mean by interfacial angle? The interfacial angle is nothing but what is the angle between the any 2 axes. X and y, it is alpha. Y and z, it is beta. Z and x, it is called as gamma. So the point of intercept made by the crystal on the 3 axes is ABC. The angle between the 2 axes is called as, that is alpha, beta, gamma or interfacial angles. Generally, if you have a cube, if you have a cubical crystal like sodium chloride, the size of the crystal in x axis, y axis and z axis, that is named as ABC, that is lattice constant or lattice parameter, one of the lattice parameter, that is point of intercepts, and another one, the angle between any 2 axes, that is alpha, beta and gamma. So these 2 factors are called as lattice parameters. They are called as point of intercepts and interfacial angles. The next one is primitive cell and non-primitive cell. So what about primitive cell? Hope you consider a cube. Okay, you consider a cube, and the cube which has 4 heads in the top, 4 heads at the 4 edges at the bottom. In the edges, you are keeping a ball. That means you are just keeping a ball. This is the simplest crystal which consists the atoms only at the corners. If the crystal or a unit cell which is made up of only corner atoms, or it is made up of only one atom or one lattice point, then it is called as primitive cell. Okay, so the number of lattice points per unit cell is 2 for a BCC and 4 for FCC. So that is a example is given. BCC means body centered cubic system, FCC means face centered cubic system. But a simple cubic system, it consists of atoms only at the corners of the cube edge. 8 cube edges, it consists of 8 atoms. But it is not the whole atom. The value of corner atom is 1 by 8. So 8 atoms into 1 by 8, that is equal to 1. So the simple cubic system is made up of only one atom. That is why we say a crystal is made up of only the atoms at the corners, or it is made up of only one atom. Then the crystal is said to be primitive cell crystal. That is primitive cell. So the primitive means it consists of atoms only at the corners, or the crystal is made up of only one atom, then that is said to be primitive cell. So what about non-primitive cell? Non-primitive means apart from the corner atoms, it has another additional atoms either in body centered or at the face centered. Because of the cube have 6 faces, so it has the atom at the 6 faces. So in addition to the corner atoms, the atoms value, that means the crystal is composed by the number of atom increases. So it is higher than one atom or more than one atom, then it is said to be non-primitive cell. It is very clear from this, a crystal is made up of only one atom, or the crystal which consists of only corner atoms, it is said to be primitive cell. A crystal is made up of more than one number of atom, then it is said to be non-primitive cell. For example, body centered cubic and face centered cubics are the example for this crystal, non-primitive crystal or non-primitive cell system. So how many crystal systems are available in the world? In these 2D or 2D systems or 3D system, there are 7 basic crystal systems are available. It is represented, or it is differentiate with respect to the value of ABC and alpha, beta, gamma. These 7 systems which are vary with respect to lattice parameters ABC and alpha, beta, gamma. They are triclinic, monoclinic, orthorhombic, tetragonal, hexagonal, trigonal and cubical system. So these are the 7 crystal systems available. Okay. Then the Bravais lattice in 14 types. So we are calling only 7 crystal systems, but in Bravais 3-dimensional crystal lattices with respect to the position of atom, the 7 crystal system is further divided, further classified or further increased as 14 types, totally 14 types. How it is possible? So one by one we will explain. So first one is for simple system, that is triclinic system. So what is Bravais lattice? 14 types. Already we have a 7 crystal system. Okay, in that 7 crystal systems, the simple system only explained, that is cubic, hexagonal, tetragonal, orthorhombic, monoclinic, triclinic, which are consist of atoms only at the corners. The which is simplest cell. So the complicated system also available, yes, available. That's why we previously discussed about body-centered cubic system, face-centered cubic system, base-centered cubic system. So these are the additional atoms available in the crystal system. That is why the 7th system is further divided into 14 types. So first one is, so simple means the atoms only at the corners. Base and body centered means apart from the corner atoms there may be a body centered atom inside the crystal system. That is called as body centered crystal system. Another one is base centered. The atoms are located only at the base. That means bottom surface base and top surface base atom. So this is called as base centered atom. And another one is face centered atom. A cube have 6 faces. So the 6 faces have atoms in the faces. That is called as face centered cubic system. So I am discussing with as an example for cubic system. That is why I said it is a face centered cubic system, it is base centered cubic system, or it is a body centered cubic system, like that. So but not all lattice systems are allowed for these 7 types. For cubic only 3 system is available, that is simple cubic, body centered and face centered. The base centered system is not available in cubic system. So the cubic system have only 3, not 4. The only system which exhibit in all 4 categories, that is simple, body centered, base centered and face centered, that is none other than that is orthorhombic crystal system. In orthorhombic only the 4 systems are available. Okay. So now first one is Bravais, that is for triclinic simple cubic system. Look here in the diagram, this ABC values are not equal. AB is not equal. So in all directions the length is different and also the angle also not equal to 90 degree. That means the angle is less than 90 degrees. So this crystal might be a small inclined one. That means it is a slope, parallelogram, like a parallelogram. So the crystal is inclined one. So the triclinic lattice has only one form, the simple or primitive system, primitive form. That means primitive means the atoms located only at the corners. For example, copper sulfate and potassium dichromate, these are all the example for this triclinic system. And monoclinic system, there are 2 systems available, only simple and base centered system. The only crystal system which exhibit in the monoclinic system apart from the orthorhombic is this monoclinic system. So here the base centered system is available. Here the ABC is not equal. Alpha beta is 90 degree, but the gamma is not equal to 90 degree. So the only one angle only not equal to 90 degree. So this is sodium sulfate, FeSO4 and NO2SO3. So these are the examples. So FeSO4 is example for simple monoclinic system and NO2SO3 is the base centered cubic system. So sorry, base centered monoclinic system. This is the monoclinic. In monoclinic the base centered system is available. So the second one, next one is the third system. Look here, orthorhombic. In orthorhombic the 4 states are available. That is simple orthorhombic, body centered orthorhombic, base centered orthorhombic and face centered orthorhombic. So the 4 lattice points, different lattice point locations are available. The allowed is for this exists in the 4 category also. So in orthorhombic crystal system, The crystal exhibit in four forms: simple, body centered, base centered and face centered. The angles are 90 degree and their axial length, that means the point of intercepts or ABC are not equal. They are not equal, but they are 90 degree. So they are sit in straight. There is no inclination in sides, so it's look like a straight crystal system. This is orthorhombic. Next one is tetragonal. In tetragonal system, the two axial lengths are equal. Only the C value is not equal. That means A and B equal and C may be height 1. But the alpha, beta, gamma values are 90 degree. That means all axes are straight. So in this system, there are two crystal systems are available. One is simple tetragonal and another one is body centered tetragonal system. So these two are the main two crystal systems in tetragonal crystals. And next one is hexagonal. So the hexagonal, like look here, those are in the hexagonal system. A and B values are equal, but C is not equal to A and B, which is higher than A and B. And the angle between A and B is 120 degree. Look here, this is very high degree, so this is 120 degree. So alpha, beta, gamma is 90 degree. Alpha, beta is 90 degree and gamma is greater than 90 degree and it is equal to 120 degree. Then only the hexagonal crystal system is possible. So in hexagonal system, simple hexagonal only available. Example, quartz and tourmaline. Quartz crystal are naturally grown and it is identified in mines in somewhere in the beneath of the earth. So the crystal which exhibit hexagonal structure. In the net there are so many crystal images, natural crystals are available, and that is quartz also one among them. And another one crystal system is trigonal or rhombohedral system. In this system, alpha and beta are equal, but gamma is not equal to 90 degree. That means less than 90 degree. So one side only it is leaned. But the ABC values are equal. Look like a cube. So ABCs are equal. Definitely it is a cubical system. But alpha, beta, gamma values, alpha and beta only equal to 90 degree and gamma is not equal to 90 degree. So calcium sulfate, bismuth, antimony, calcite, these are all the example for a trigonal or rhombohedral crystal system. Finally, cubical crystal system. What about cubical system? Cube means all sides are equal and also they are a straight lined one. So the angle between the two axes is 90 degree. So alpha equal to beta equal to gamma equal to 90 degree. Then A equal to B equal to C. So this is the lattice parameter values. In cubical system, it is available in three forms, that is simple cubic system, body centered and face centered cubic system. So this is the diagram which represents the simple cubic, body centered and face centered cubic system. So these are the fundamentals of crystals. And next we are going to move how the crystals are characterized. How the crystals are grown first. These are the fundamentals, and we grown the crystal like slow evaporation technique, like a salt. The salt is grown in the seabed areas. The seawater is slowly evaporated. Then the salt crystals are formed. Sodium chloride crystal is formed. This is the simple technique available in the world to grow a crystal. Like that, some components, some minerals which are added in a particular solvent, it is dissolved and it is kept in a sunlight area, and the solution is evaporated, and slowly the solute which are formed as a precipitate as a crystal form. So this is called as crystal growth of slow evaporation technique. So now we are going to study about the structural and optical properties of potassium magnesium sulfate single crystals. For that, the potassium magnesium salts which are dissolved in a particular solvent and in at particular molar concentrations, because of they have some molecular weight. So particular 1 mole of substance is dissolved in 100 ml of solution, like organic solvents like ethanol, ethylene glycol, whatever it may be, some organic solvents. And now it is dissolved and it is kept in a sunlight, slowly evaporated, allowed. Then finally the precipitates are formed, which are nothing but small crystals. We have taken the crystals and we have to examine it whether the crystal is perfectly grown or not, and what is the crystal system, what is the lattice parameter values, how the crystallography structure is derived by this method, whether the material element is potassium and magnesium or not, or any other foreign impurities are there, any crystal defects are there, and how to characterize their properties like mechanical, optical, electrical, and what are the morphological details. That means how structure is this. The crystal structure we know very well, but morphology means outside look, how it look like. It look like a rod or a ribbon or a what we say, different shapes, rod, nut, wall, cylinder, cone. So how it exhibits the morphology, that is measured by some microscopic techniques. There are so many microscopic techniques are available, SEM, TEM, FE, SEM and AFM, which are all available. So first one, in this part we are going to discuss about how the crystal is grown and what is the structural analysis XRD, and what about the optical property by UV vis NIR spectral analysis, ultraviolet, visible, near infrared spectroscopic analysis. And next one is functional groups present in the crystal, that is how the atoms are located and how the atoms are bonded with another atom, what type of bondings are available, what type of molecules are there. This is identified by using FTIR techniques. And next one is EDAX analysis. EDAX is the energy dispersive analysis of X-rays. So with respect to the energy value, what are the elements present in the sample, this is compositional analysis of a sample. So how much of potassium atom, how much of magnesium atom present in the sample in 1 mole substance, what percentage is this, and this potassium and magnesium is present in the sample or not, that is analyzed by EDAX. So these are the optical properties such as refractive index and absorption coefficient. So this is independent of light intensity. The principle of superposition, the fundamental tenet of classical modes. So look here, so I cannot read the PPTs and I just go through this morphological data, and this is the grown crystal, and potassium and magnesium salts were dissolved in the perfect solvent, and it is kept in sunlight, shaded room, and it is closed by a paper, and a small drill is put on the top of the paper. So that's why the air circulation will allow the solution to evaporate slowly, and the crystals are grown at the bottom side. So this is the grown potassium magnesium sulfate single crystals. Look here in a graph sheet, it's look like nearly 1 to 1.5 centimeters, 1 to 1.5 centimeter of a crystal, but the morphology it not look like a well structured crystal. That means this is a agglomerated crystal system. That means many crystal systems which are formed, that is why the shape is irregular. But we can break it, or we can examine it by using X-ray. We can get the structure. So what is the analysis XRD data? So the single crystal XRD data, which gives the unit cell dimension, that is A equal to how much, 9 Armstrong unit, and B equal to 12.24 Armstrong unit, C is equal to 6.095 Armstrong unit, and whatever the value of alpha, beta. So alpha and gamma is 90 degree, and only one system which is 104 degree. So only one axis is not equal to 90 degree. So you can check this. Any two angle is 90 degree, one angle is not equal to 90 degree. That means which exactly match with the monoclinic crystal system, and the density value is 2.025 gram per cubic centimeter. And so what is the volume of the unit cell is 674 Armstrong cube. So this is the value of crystal. And now look here, these are the XRD pattern of the grown potassium magnesium sulfate crystals. In this diagram, this x-axis which represent the degrees. What is the value of degree? That means the angle of diffraction, in the incident angle and the diffraction angle, the two theta value. So how it differs? Then the peak values which represents 431, 231, 151, which are represents the crystal planes, lattice planes. These are called as Miller indices. The value is Miller indices. Okay, now these standard patterns which are compared with the ICDD data, International Diffraction Data, International Crystal Diffraction Data, which is available, and it is compared with this potassium magnesium sulfate crystal analysis, which gives this comparison is well matched with the literature value, and it is a reported value. These peaks are corresponding to these PMS crystal systems. So definitely the grown crystal or the given crystal is PMS system, potassium magnesium sulfate crystals. And now here the UV vis spectral analysis which are given, and around the value of UV light at 200 nanometers. So in this area, the excitation wavelength which starts at the ultraviolet region. So near 200 nanometer means it is ultraviolet region. So the transmittance is very high. So the crystal must be suitable for the high optical applications, photonic and optical applications. So this is the energy band gap value determination. From this UV, we are calculating the energy band gap of this material, that is 6.4642 electron volts. This much of high voltage. So this is high value of energy band gap. So the value of energy band gap is very high. And now, so the lower cutoff wavelength is obtained at 192 nanometer. So it is in the ultraviolet region. So The band gap calculated was 6.462 electron volt. So FTI spectrum of EMS crystal, and it shows that 3 broad peaks at 3550 and 1117 and 624. So these are the dominant peaks. So it is how it is analyzed means these crystals were mixed with the KBr powders, potassium bromide powders, and it is mixed and it is kept in a sample holder, and the IR rays are passed. Then from the output we are analyzed what is the function groups present in the sample. So the absorption peaks observed at 3550 and 2087, which are due to the OH symmetrical stretching, and the peak at 1624 is due to OH asymmetric stretching, and the peak observed is 624, that is assigned to be SO42 minus group. So from this data, all the functional groups which are present as expected: potassium, magnesium, sulfate crystals. So the sulfate group also present and OH group also present, and so the functional groups easily identified. So look here, these are the functional groups present in the sample, and now it is the energy dispersive analysis of X-rays, and the K is for potassium and O is for oxygen, Mg for magnesium, and S for, that is, sulfur. So these elements which are conformed by this test, so the crystal is composed of potassium, magnesium, sulfur and oxygen. So finally we come to the conclusion that the ground crystal has sufficient amount of volume, nearly 1.5 centimeters long, and the crystal is potassium magnesium sulfate, is a transparent one, good quality of transparent, and the lattice parameters are found by using XRD method, ABC and alpha, beta, gamma, and which confirms that this crystal is from monoclinic system, and the functional groups were identified in a FTI spectrum, and the UV transmission spectrum shows a wide transparency window, making it a potential material for NLO applications. So the potassium magnesium sulfate crystal is suitable for fabrication of various optoelectronic devices. So these are all the characteristic techniques available, how we interpreted the data and what we found the crystals characteristics, how the structure is, how the shape is, how it is bonded with another atom, and these are all the informations gathered from the XRD. And FTI functional groups, that means the bondings between the atoms and molecules, how it vibrates, and the UV spectrum which confirms that it's emission light, then how it behave when the light is passing through it. So it's a transparent material, and it is its transparency also maximum. So the light is emerging to the system and it is coming out without any damage or without any low efficiency. So it is come out as it is passed as it is. So there is no variation of the input and output signal, and it can be used for non-linear optical property applications. So this potassium magnesium sulfate crystal is suitable for the fabrication of various optoelectric devices. So these are the today's summary. What is crystal? What are the basic definitions of crystals? And what are the characteristics of crystals? Then how the crystals are grown? Then how the crystals are analyzed by using experimental techniques? How can we identify the components and the compositions of the crystal? Then next, how the crystal is suitable for optical, electrical, magnetic, and etc. properties applications. So now we discussed as an example for only PMS crystals which are suitable for non-linear optical property applications. So this is a simple method of grown crystal by using slow evaporation technique, and how the crystal is useful for the application oriented as a device level. In device, how can we use these crystals? Because it gives the input signal as an output, so without any decreasing the intensity, so it gives the same intensity, so it can be useful for optical instruments also. So these are the points we gathered from today's lecture. Thank you one and all. Thank you very much.